Thank you. Well, it's a great pleasure to be here and join in the celebration of Stephen's birthday. I first met Stephen in the early 1980s. I was a young postdoc at the Institute for Advanced Study in Princeton, and Stephen came for a visit. And to my surprise, one day I get a message that he wants to see me. So I nervously enter his office, and he starts asking me about work I was doing with Malcolm Perry about how to extend Witten's proof of the positive energy theorem to include black hole boundaries. And it turns out that Stephen was working with Gary Gibbons on exactly that same problem. And so in the end, we decided to join forces and wrote a paper in '83 proving this extension. Well, sometime during this collaboration, Stephen started to tell me about the Lucasian chair of mathematics that he was given in 1979. And he explained to me that before him, the chair was held by a man named James Lighthill, who was doing fluid mechanics. And before that, it was Dirac. And before that, it was Larmor. And before that, it was Stokes. And he kept going farther and farther back into the past, all the way to Newton. He knew all the past chairs of this Lucasian professorship. Well, Stephen, of course, has made many fantastic contributions to our field, but perhaps his greatest contribution is the discovery of Hawking radiation, the fact that black holes radiate. It really started the whole field of quantum black holes, which has dominated this field for over 40 years. So what I'd like to do today is to tell you about two recent insights into quantum black holes. One which tells us something that we didn't know before, clearly a step forward, but the other calls into question something that we thought we understood, and hence perhaps a step back. So let me start with the good news. And this is work I did with my former student, Netta Engelhardt, and described in a couple papers. And this uses the idea of holography. So let me just spend a minute reminding you what that is. The early motivation that quantum gravity might be holographic came from the Bekenstein-Hawking formula for the entropy of black holes. Most systems, of course, have an entropy which grows like the volume, but they argued that black holes are different and have an entropy which is proportional to the surface area, suggesting that everything that happens inside a black hole could perhaps be described by degrees of freedom living on the boundary, the horizon. In the early 90s, Tufte and Susskind suggested that this was a much more general property of quantum gravity, and that, in fact, everything that happens in a region of space could perhaps be described by degrees of freedom just on the boundary. Well, the first concrete formulation of this holographic idea came through this gauge gravity duality, also known as the ADS-CFT correspondence. And that says that with anti-de Sitter boundary conditions on your space-time, string theory, which of course includes gravity, is completely equivalent to a non-gravitational gauge theory living on the boundary of space at infinity. At first sight, of course, this seems completely crazy, but it's not obviously wrong, because when one theory is weakly coupled and we understand it well, the other theory is strongly coupled and we don't have much intuition about its properties, and vice versa. Well, by now there's overwhelming evidence in favor of this, but of course no rigorous proof. I'm simply going to assume it and ask what it tells us about quantum gravity. Well, a powerful feature of this duality is that statements that are easy to establish on one side often imply highly non-trivial results about the other side. So, for example, the fact that the formation and evaporation of black holes must be unitary follows from the fact that it is describable, according to this duality, by an ordinary Hamiltonian evolution of the dual field theory. And I would now like to tell you about a couple of other insights, apparently non-trivial statements, that follow just from simple properties of the dual field theory. So the first is cosmic censorship. Now, Mihalis gave a very nice discussion of this yesterday, in which he mentioned, for example, that the weak cosmic censorship, as he called it, says that generic asymptotically flat initial data has a maximal evolution that contains a complete null infinity. So in other words, weak cosmic censorship says this can't happen. You can't have initial data which evolves to some event like a singularity which cuts off evolution at a finite retarded time so that you get only a part of scry in your maximal Cauchy development. Now, it was always hoped that if cosmic censorship should fail, quantum gravity would somehow resolve this singularity so evolution could continue. After all, that was one of the reasons we wanted quantum gravity to somehow resolve some of these singularities. Well, in holography, we just know that's true. This is an asymptotically anti-de Sitter space-time. The boundary, the conformal boundary at infinity, is time-like and not null because of the negative cosmological constant. And whatever happens in here, even if you form a naked singularity classically, evolution in the dual field theory will continue. And this tells you that quantum gravity does resolve these naked singularities. We have examples of classical initial data which form naked singularities. These are direct analogs of the Choptuic critical phenomenon, also discussed by Christodoulou, which says that special initial conditions, and say the collapse of a spherical scalar field, will produce a naked singularity, and even in that case, quantum gravity is going to resolve it. There's no doubt about that. To tell you about another consequence, let me start with an obvious or simple question. When can two quantum field theories communicate? Well, normally we think that if they're defined on separate spacetimes, they can't send signals to each other. So here are two copies of Minkowski space with the conformal null infinities attached. This is now ordinary flat Minkowski space. And the ordinary quantum field theories, and we say clearly you can't send a signal from this quantum field theory to that quantum field theory. Well, actually, when these quantum field theories are conformally invariant, there's a subtlety. Because a conformal field theory can be mapped to an Einstein static universe, or a static cylinder. And if you have two copies of Minkowski space, you can either conformally map it to the same Einstein static universe or to two separate ones. Clearly, in this case, you can't send signals from one to the other, but in this case, you can. They just become part of a larger conformal field theory. Well, I'm going to consider conformal field theories which are defined on a static cylinder themselves. It's defined on the space-time, which is a sphere cross R, and in that case, we don't have to worry about this subtlety. Two conformal field theories on this static cylinder cannot be conformally mapped to a single larger space-time because this infinite static cylinder is conformally maximally extended. And this leads to a simple consequence in the context of holography. We call it the no transmission principle, and it simply says that if two conformal field theories on this static cylinder have gravity duals, then no signals can be transmitted between their bulk duals. If you can't send signals between them on the boundary, you can't send signals between them through the bulk. So, for example, if you take the standard Schwarzschild anti-de Sitter spacetime, this is the usual Penrose diagram that we saw earlier in Douglas's talk this morning, and you just put two copies of it and ask, could you possibly, in quantum gravity, resolve the singularity in such a way that a signal could enter the black hole and emerge through the white hole and go out to this asymptotic region? Well, the answer is clearly no, because that would violate this no transmission principle. Now, maybe this isn't too surprising. I don't know anyone who ever suggested that quantum gravity might do that. But as Michaelis said yesterday, this is a very, very special black hole. It is not at all generic. Generic black holes are either rotating or charged. And when you think about a charged or rotating black hole, you seem to get into a puzzle, because classically, you can send signals from an asymptotic region here through the black hole and have it come out in an asymptotic region there. Okay, so that seems to violate this idea. But we've known for a long time that this inner horizon is unstable. If you send a signal in, you're going to perturb the black hole. And so this will become a singularity, and you don't get the signals going through. But as Michaelis again discussed yesterday, in the asymptotically flat context, it is now known, and de Fermos was the one to prove it first rigorously, that this singularity that forms in the Reiser-Nordstrom case, and he claims to have a proof coming out, I guess, in the Kerr case soon, that this is actually a very weak singularity in the sense that the metric can be continued in a continuous manner as a Lorentzian metric through that boundary. It is true that the Christoffel symbols are not square integrable, so you can't uniquely solve Einstein's equation. It is a boundary to the Cauchy evolution, but it seems like a rather mild, a weak null singularity, as people say. And now you say, okay, let's now go to full quantum gravity. It's not at all, this is just a pretty weak singularity. Maybe you could resolve that. Well, the no transmission principle implies that you cannot do that in full quantum gravity. If you could, you would violate this principle. You would send signals from this conformal field theory to another conformal field theory defined on a completely separate space-time. So this is starting to sound like a less trivial consequence. I should mention that, well, the results in asymptotically flat space depend on the fall-off of fields, which is much faster than in ADS. In ADS, fields don't die off as fast. That might suggest that the singularity in this case is stronger than the one that's seen in the asymptotically flat case, and so that might be part of the reason why quantum gravity can't resolve it in this case. But anyway, this is certainly a consequence. Now, there's one more thing. If you can consider certain singularities in the conformal field theory itself. In other words, there's conformal field theories whose evolution ends in a finite time. And if the evolution ends in a finite time, then the evolution in the bulk has to stop as well. In other words, a gravity dual to one of these singular conformal field theories must have a cosmological singularity, a singularity that goes across all of space, and that singularity cannot be resolved in quantum gravity because you would again have a violation of this duality. Well, a few comments. You might say, well, why don't you just put some couplings between the conformal field theory here and the conformal field theory there? That way you can send signals from one to the other. But clearly that would cause all sorts of causality problems, because if you could send signals from here to here through the couplings, you could do the same thing in reverse, and that would introduce problems with causality violation. You could just make up a rule and identify a state in one CFT with a state in the other and say, okay, that's how we're going to transmit signals. But that would be extra input, not part of the original CFTs, and that would violate this duality that they're supposed to be equivalent. The bulk is supposed to be equivalent to the dual field theory. And finally, you can show that there's just no natural way to identify the states. In the black hole case, if you try to take some limiting asymptotic state at large time and use that as your input for the next CFT, well, the black hole state doesn't settle down, right? Unless it's an exact energy eigenstate, it's going to be evolving, and phases are going to change and all sorts of things. So you don't have a unique state to pick out at late time. OK, let me now go to the step back, the bad news. And this is based on recent work with Kunduri and Lucetti. And to start, I'm going to take you back 20 years. This was the middle of the so-called second string revolution, which saw a number of just amazing discoveries, including this gauge gravity duality, which I mentioned. That was also 20 years ago. But before that, we had the first precise counting of black hole microstates. And this all started with the famous paper of Strominger and Vafa in January of 1996, where they reproduced the Hawking-Bekenstein entropy of a static, extremal, 5-dimensional black hole by counting microstates of string theory. And it was just fantastic. It was tremendously exciting. That immediately followed a month later with the generalization to a rotating 5-dimensional extremal black hole by Breckenridge, Myers, Peat, and Vafa, now called this BMPV black hole. And within months, there were proofs of, or counting of 4-dimensional extremal black holes, and near-extremal black hole entropy was also reproduced in both 4 and 5 dimensions by counting microstates in string theory. So this was just a tremendously exciting period. We had, finally got an insight into the microstates that make up black hole entropy. Well, let's fast forward to recent times. And a couple years ago, I guess Kunduri and Lucetti found a new family of extreme rotating black holes in 5 dimensions. Like the BMPV black hole, it's asymptotically flat and can have exactly the same asymptotic charges. It differs from the BMPV black hole because there's non-trivial topology outside the horizon. There's a non-contractible two-sphere entirely outside the horizon supported by magnetic flux. And so it differs in that way. And the surprise is these new black holes can have greater entropy than the original BMPV black hole. So this raises a puzzle. Back 20 years ago, the microstate counting was thought to include all the bound states of strings and branes with the given total charge. And you count them up, sort of the maximum configuration with all those charges when you go to strong coupling is the black hole. Well, now we have another solution, which is a black hole with bigger entropy than the BMPV. And so you can ask, why did the original counting give the entropy of BMPV black hole and not this new family of black holes? Well, this is not the first time the question has been raised. There are some other examples of solutions with greater entropy than this BMPV solution, but they either involve more than one horizon or are not asymptotically flat. So for example, in 5 dimensions, there's something called a black ring, a black hole with a horizon topology S2 cross S1. A single black ring can't have the same charges as the BMPV black hole, but if you take 2 black rings, 2 concentric black rings, you can show that you can have the same charges as the original BMPV black hole and have greater entropy. But these new black holes are the first examples of asymptotically flat single horizon black holes with the same charges but greater entropy. So it makes the question more acute. Well, let me just say a few words about what these black holes look like. So they are solutions of the so-called 5-dimensional minimal supergravity action. And you recognize the standard Einstein action, a standard Maxwell field. In fact, you need a Maxwell field in 5 dimensions to have supergravity. And then you have to add this Chern-Simons term. That's required by supersymmetry. But that's it. So that's this sort of the bosonic part of the 5-dimensional supergravity action. And it's been known now for many years that there's a large class of stationary, non-singular solutions called bubbling geometries. These have been proposed as possible microstates of black holes, these classically non-singular solutions, and they're part of the so-called fuzzball program to understand black hole entropy. These have been discovered by many people over the past decade or more. And they have non-trivial topology. That's key. They're, in fact, all contained in these sort of lots of non-contractible spheres supported by magnetic fluxes scattered around space. These solutions are all supersymmetric. And one of the things supersymmetry does for you is simplify the equations. So in fact, you can describe them in terms of harmonic functions. Or at least there's a class of them that can all be described by just simple harmonic functions. I should mention that it's recently been shown that this class of bubbling geometries are likely to be non-linearly unstable, work done here. But I'm not going to worry about that for the moment. I'm just going to take them as solutions, unperturbed solutions. OK, so there's no black hole here. These are just all, in fact, they were touted as being great because they had the same charges as black holes, but there's no horizon. So they're totally non-singular. Maybe these are the microstates. Well, you can add a spherical extremal black hole to any of these geometries, keeping the non-trivial topology outside the horizon. So because it's all determined by harmonic functions, it's actually easy to write down these solutions quite explicitly. So we're going to consider the simplest case. We're outside the spherical horizon. And of course, in 5 dimensions, the horizon is a 3-sphere. So you have an S3 on the horizon. And outside, there is another 2-sphere, which is not contractible. The solution is described by 4 numbers. You have the total charge. You have 2 angular momenta, because in 4 space dimensions, you have 2 orthogonal planes, and you can have independent rotation in each of those 2 planes. So you get angular momenta J1 and J2. And then you have another parameter Q, which is a measure of the flux through the 2-sphere. The mass is not an independent parameter because of supersymmetry. The mass is completely determined in terms of the charge. So I should say, these solutions are of interest because we've learned that black holes are not unique above 4 dimensions. But this is the first example where you have continuous non-uniqueness. You have this parameter Q that you can vary, which is not an asymptotic charge. It's something that you sort of see more locally. It's a continuous family of solutions with a spherical black hole and the same total charges at infinity. It's quite a dramatic illustration of the lack of uniqueness in higher dimensions. OK, well, we want to compare with the BMPV black hole, and that solution has equal angular momenta in the 2 planes. So we're going to require that J1 is equal to J2. And then there's a scaling symmetry in the equations. And so to remove that overall sort of scaling symmetry, we'll normalize these parameters by the total charge. So we're going to work with some dimensionless parameters, eta, which is a measure of this normalized angular momentum, nu, which is a measure of the this sort of flux, parameter little q, and then there's the area of the horizon, which of course will be an important quantity. Again, we'll normalize that. And the thing to note is that in these, I'm dropping factors of 2 and pi, which are irrelevant. But with these rescaled variables, the extremal limit is the rotating black hole. It has a maximum angular momentum for a given mass. The extremal limit is eta equal to 1 in these variables. OK, so you can ask, we have a family of solutions. What range can these parameters eta and nu take? And you find that they have to lie inside this triangular region where I plot eta on the vertical axis and nu on the horizontal axis. The boundaries, so this curve in blue is just a case where the black hole, and we've inserted a spherical black hole, the size of that black hole shrinks to 0 along that curve. It also shrinks to 0 along this curve. And this third leg is not where the black hole shrinks to 0, but you run into problems outside the horizon at one of these so-called centers. So you have harmonic functions, and they have standard poles at various places. And the solution, in order to be regular there, has to satisfy some conditions, which break down along a curve which looks like this. Now, you can ask, OK, there is a smooth solution without the black hole. We stuck the black hole in. What do you have to do to get back to that smooth bubbling geometry? And turns out you need to go up to this corner. So this point P corresponds to the smooth solution. If you take the black hole to 0 in any of these other directions, you just get a singular limit. The other thing to note about this is that the extremal limit for the standard BMPV black hole is eta equal to 1. And so these new solutions clearly extend into a region with more angular momentum than the previous solution had. Well, what about the area? For BMPV, the area is very simply expressed in terms of the angular momentum, just the square root of 1 minus eta squared. And the formula for the area of the horizon of the new solutions is much more complicated. I'll spare you the details. But it also depends on this flux parameter nu. Well, so you can plot it. So here's the horizon area for the BMPV black hole, which is in blue. And the new black holes is in yellow. And there's clearly a region where the new black holes have greater area than the old black holes. And they have exactly the same charges. So I should point out that if you look in detail about what, okay, so here's eta going back this way. The nu is in this direction. The area is plotted vertically. But if you look at the numbers here, eta is very close to 1 before you see the new solutions having a greater entropy. The numbers here are 0.998, 0.999, and going up to 1. Okay, so you have to be very close to the extremal limit of the old solution before you see this enhancement. Okay, now from a gravitational standpoint, there's a very simple explanation for both the fact that you can exceed the usual extremal limit and the fact that the new solutions have greater entropy. It's really not a surprise at all. The old solution, this BMPV black hole, had 0 entropy in the extremal limit. When eta goes to 1, the entropy here goes to 0. The new solutions have structure outside the horizon, this non-trivial topology, which can carry some of the angular momentum. So when the total angular momentum approaches the maximum for BMPV, the angular momentum carried by the black hole can be less than that. And so it can have bigger area. It will not be extremal as a local black hole, in the near horizon region. And also, well, you have entropy. The near black hole has less entropy. You can exceed the total angular momentum as well by, well, for that reason. Okay, so just because you have structure outside which is carrying some of the angular momentum, you can have more angular momentum and have black holes with greater entropy. But we come to the counting of microstates. Where are the microstates of these black holes? Now, most of the counting of microstates in the starting with Strominger and Vafa's famous paper, was based on taking a weak coupling limit and looking at the states of strings and branes in Minkowski space. So you might say, oh, well, if you have Minkowski space, you can't have any non-trivial topology. So clearly, solutions with non-trivial topology aren't going to be seen in a perturbation expansion of string theory about Minkowski space. But that's too quick, because it's been argued that this non-trivial sphere with magnetic flux, when you reduce the coupling and you reduce the gravitational effects, actually shrinks down and can be described in weak coupling as certain wrapped branes and things like that. That's been seen in other contexts. So it really looks like there must be a more complicated bound state of strings and branes and weakly coupled string theory that have greater entropy than the configurations that were looked at before and used to reproduce the BMPV black hole. And this sort of remains to be found. Okay, so let me summarize this quantum black holes. The one step forward was that gauge gravity duality implies that quantum gravity cannot resolve the singularity inside certain black holes. And then we've seen that there are gaps in our understanding of the entropy of certain extremal black holes in terms of counting microstates in string theory. Now, I was told by somebody earlier in this meeting that I should not call my talk one step forward and one step back. It says not only does that sort of imply that we've made no progress, it suggests that we're moving in the wrong direction. So to end on a more positive note and to encourage more steps forward, I'd like to announce that due to the generosity of an anonymous donor, we have now set up a new postdoctoral fellowship series at the University of California, Santa Barbara, which we're calling Fundamental Physics Fellows. So the first applications will be considered this fall for a position to start a year from now. And preference will be given for applicants working in quantum gravity. This donor actually is interested in all the work we're doing involving quantum black holes and all the exciting questions we're trying to answer. So this is just being set up at the moment. Please see the UCSB Physics Department website or contact me sometime in September when we have all the details arranged. And let me end by just wishing Stephen a very happy 75th and a half birthday. Thank you very much.
I pass to Raf, but I'm going to abuse my position by actually giving a comment and a question.
Yes.
So, in a sense, one of the nicest ways of counting the states in the D1, D5 is to think in terms of the 6-dimensional language and two-dimensional conformal field theory.
Right.
But the 2D CFT emerges when you go to the Higgs branch of the D1, D5 system. Right, it only counts the states on the Higgs branch. It only counts things where you have the structure near the horizon. So would your extra states actually come from states on the Coulomb branch?
I don't know.
Because that's the most natural explanation. I should say, in the fuzzball story, the microstate story, there is evidence, we have evidence which will appear at some point. David's laughing at me. It will appear at some point that some of these bubbling states are actually Coulomb branch configurations.
Well, that is good. I mean, we did look into this a little bit and was a little surprised that we didn't know, apparently, what the dual field theory states to these bubbling geometries were. And so we couldn't even use this ADS3, S3
right. Exactly.
Insight, this decoupling limit, to get insight into what these new states are. But if you have evidence for that, that could well be relevant.
So this is sort of probably the most conservative, I would say, solution to your puzzle. Now I'll go to Raf first.
So even before your final remarks, I was going to say you should have called it 2 steps forward, because I think identifying an interesting problem is always a step forward. And in that spirit, I'd like to just loop back to Stephen in 1974 and 1976, where I think he identified a hugely interesting problem. And we're not doing it justice. I think when we say that something like ADS-CFT, which certainly gives huge evidence for unitarity, resolves this problem. Because it just tells us that the answer is probably unitarity, but it doesn't tell, Stephen told us exactly what the Hawking radiation is entangled with and purified by. It's the inside Hawking quanta. And you have to explain, because in quantum mechanics the purification is unique, you have to explain how that gets out.
Absolutely.
So that gave me an opportunity to also comment on Andy's talk. and that's done, that's where the heavy lifting is. That's why we speak of crazy things like firewalls or ER equals EPR, which are really hard to make any sense of. But that's because that problem is so hard, and it's not until we've addressed that problem. We're not going to address that by positing a pure quantum state on the outside. Then it's always easy to lose some of that information by not being careful.
Okay. Well, I didn't say that gauge gravity duality solves the black hole information puzzle. I simply said it tells us the answer is unitary. But yes, of course, there's a big question left to understand there.
Is this related to the entropy enigma that Moore and Denef were talking about?
Yes.
Also had states that...
Yeah, exactly. So I said that there were other examples where configurations had greater entropy than the standard black holes with the same total charges. And in 4 dimensions, this entropy enigma has more than one horizon. So it's not a single horizon example. But if you allow separate spherical black holes, yes, they had examples with more entropy in that case as well. Yeah.
And those are effectively also Coulomb branch. Yes, so it is the same
Yeah,
thing.
so that's
okay.
interesting.
Perhaps in view of the time, again, we'll postpone other questions for lunch, and thank Gary again.